Hi everybody, it's Professor Mitchell. We are continuing with Chapter 1, an introduction to problem solving, and today we are looking at explorations with patterns. So the objective in this section is to find patterns and determine if a pattern holds. Another objective is to talk about deductive and inductive reasoning and when to use them. We will also talk about different types of sequences such as arithmetic, geometric, and Fibonacci. And we will find the nth term of certain sequences. Finally, we will use differences to find a pattern for sequences that are neither arithmetic nor geometric. So here's an example. They want us to describe any and all patterns that you see in this sequence of problems that you see here. And of course, there are several different answers. If you notice that each of these problems that's written down is an addition problem, that means that each of those equations has two addends, terms that are being added, and they also have a sum, which is the number on the right-hand side. So if we start with the easiest pattern, we could say that the first addend, the first term in the sum, is a natural number. It's the nth natural number. It goes 1, 2, 3, 4, 5, going down this way. So that's probably the simplest one. Next, we could look at the second addend, the second term in the addition. That is a product, remember that means multiplication, of two numbers. The second of those numbers is a 9. And the first of those numbers, that's a little more complicated pattern. The first one is 0. And after that, the number is formed using natural numbers and including one more, tacking on the next natural number as the newest digit. So it goes 0 and then 1 and then 12, attaching a 2 on there, and then 123, attaching a 3, and then 1,234, attaching a 4. And then finally, the sums in these equations are just made up of a whole bunch of ones all stuck together, right? 111, 111, 1,111. So, I mean, this is a pretty cool pattern, right? It seems to be saying that if you start with the nth natural number and then add 9 times this thing, however you want to describe it, you will come up with a number that is all ones. So a good question to ask is, does that pattern hold up? I mean, will it continue indefinitely? Unfortunately, the answer is no. By the time you get up to 13, notice that eventually you run out of digits, right, to put in this number. And so one thing you can try is attaching 1, 0 for 10, and then 1, 1 for 11, and then 1, 2 for 12. And the number that you get in the end starts off with a whole bunch of ones, but then after that, it kind of goes a little wonky. So that pattern does not hold up. Holds up for a while. It's still kind of cool, but it doesn't hold up forever. So this pattern breaks down when the pattern of digits in the number being multiplied by 9 contains previously used digits. All right, next let's talk a little bit about inductive reasoning. Inductive reasoning involves making generalizations based on observations and patterns. Inductive reasoning may lead to what's called a conjecture. I remember when I was kind of first learning this stuff, I had a teacher who described a conjecture as a mathematical guess. So it's sort of a theory, hasn't been proven, a statement that is thought to be true but hasn't been proved. And a conjecture can be proven false by what's called a counterexample. And that's a statement that contradicts the conjecture. So in the previous example, The conjecture could have been, if you keep up this pattern, you will always get a sum that contains all ones as its digits. And that example that we looked at the end was a counterexample. It showed that that doesn't always work. Here's another little something that I picked up somewhere along the way. I'm sure it was in a class that I took. It's a way to help you remember the difference between inductive and deductive reasoning. So the abbreviation is PIG, like pig, and that stands for particular, inductive, general. So when you go from a particular example to a general statement, that is inductive reasoning. Deductive reasoning is going the other way. It's going from a general principle to a specific example. All right, so here's another example of the danger of making conjectures. In this problem, we will choose points on a circle and connect them to form distinct, non-overlapping regions. So in this figure that you see at the bottom, 2 points determine 2 regions. See, they've put 2 points on the circle, connected them with a line, and that line divided the circle into 2 regions. Next, if we put 3 points on the circle and we connect all of those pairs of points, that divides the circle into 4 regions. And if we put 4 points on the circle, once you get to a certain number of points, you have to be careful about avoiding symmetry. See, this is supposed to be any arrangement of points. So it's good when you're drawing these pictures to not make the points evenly spaced, so that basically what you want is to get the maximum number of possible regions. See, if I drew a line, let's say that I added a point, let's say that I added points here right next to this 2 and down here right below this 4. I would not want a line that goes right through this point, because that would not give me the maximum number of possible regions. All right, so I want to stagger those points in a sort of irregular pattern. But in this case, 4 points does give you 8 regions. You can see the 8 regions there. So the question that they're asking is, what is the maximum number of regions that would be determined by 10 points? So it looks like there's a really clear pattern to this, right? When you have 2 points, you get 2 regions. When you have 3 points, you have 4 regions. When you have 4 points, you get 8 regions. The number of regions seems to be doubling every time. All right, so again, it appears that each time we increase the number of points by 1, we double the number of regions. If this were true, then for 5 points, we would have 2 times the number of regions with 4 points, which would be 16, and so on. If we base our conjecture on this pattern, we might believe that for 10 points, we would have 2 to the 9th power, which is 512 regions. Going back to the picture, let me just point out, 2 to the 1st power is 2, 2 to the 2nd power is 4, 2 to the 3rd power is 8. So it's 2 to the power number of points minus 1, okay? All right, and that does work for 5 points. You can see in this picture here. However, and at this point, it starts to get really difficult to draw this diagram. For 6 points, the pattern predicts that the number of regions would be 32. However, and take this as a challenge if you'd like, no matter how you choose these points, you will never get more than 31 regions. See in this picture, tiny little region right there is region number 31, okay? So that's kind of infuriating, isn't it? It goes 2, 4, 8, 16, and then 31, all right? So unfortunately, our conjecture is not true, all right? The number of regions is not 2 to the power n minus 1. Okay? And unfortunately, that means we're not going to be able to answer their original question. How many regions would there be with 10 points? I actually did a little bit of research when I was getting ready to make this video. I thought, that's so annoying, you know, not answering the question. And I remember doing this problem at some point quite a while ago, and I had to think for a while about how to do it. It's a somewhat complicated problem. I would be happy to talk about it if somebody would like to hear more about it, maybe in the discussion boards. But really the point of this example was just be careful about making conjectures. It may look like you have a really clear pattern, but that pattern doesn't hold up. So now let's talk about arithmetic sequences. First of all, a sequence is an ordered arrangement of numbers, figures, or objects, all right? And so in a math class, not surprisingly, we will mostly talk about ordered arrangements of numbers. Sequences can be classified by their properties. So an arithmetic sequence is one particular type of sequence. It is a sequence in which each successive term is obtained from the previous term by addition or subtraction of a fixed number, which is called the difference. So here's an example of an arithmetic sequence, 2, 5, 8, 11, 14. To get the next term, you just add 3. 2, and then 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, all right? So any sequence where you get the next term by always adding or subtracting the same number is called arithmetic. Notice how I'm pronouncing that. I'm saying arithmetic and not arithmetic. Arithmetic is a noun, and it means, you know, doing addition, subtraction, multiplication, division. Arithmetic is an adjective. So it is a type of sequence. All right, so here's an example of using an arithmetic sequence. They want us to find a pattern in the number of matchsticks required to continue this pattern. So you can see how the matchsticks are being put together. Here's the first one, uses 4 matchsticks. And then in the second one, we keep the original 4 and then we tack on another 3. And then in the third one, we keep the original, you know, these 2 squares here, and we tack on another 3. So you can see why this is arithmetic, because you're always adding 3 more matchsticks. Note that the addition of a square to an arrangement requires the addition of 3 matchsticks each time. Thus, the numerical pattern obtained is 4, 7, 10, 13, 16, 19, which is an arithmetic sequence with a difference of 3. Okay, the next example, find the first 4 terms of a sequence given by a sub n equals 4n plus 3, and determine whether the sequence seems to be arithmetic. So finding the first 4 terms is very, very easy. Just replace the number n with the numbers 1, 2, 3, 4. So in the first term, you get 4 times 1 plus 3, which is 7. Second term is 4 times 2 plus 3 equals 11. Third term is 4 times 3 plus 3, which is 15. And the last term is 4 times 4 plus 3, which is 19. So from the first 4 terms, 7, 11, 15, 19, the sequence does seem to be arithmetic, and it has a difference of 4. So to get to the next term, you always add 4 to the previous term. All right, continuing this example, find the first 4 terms of a sequence given by a sub n equals n squared minus 1, and determine whether that sequence seems to be arithmetic. So the same way, we'll replace n with the numbers 1, 2, 3, 4. Here's what we come up with. I'll leave it to you to check this math. We get 0, 3, 8, 15. And that sequence is not arithmetic because it has no common difference. The difference between these 2 terms is 3, between these terms is 5, and between these terms is 7. So that is a sequence, but it's not an arithmetic sequence. All right, next example. The diagrams in the figure below show the molecular structure of alkanes, a class of hydrocarbons. C represents a carbon atom, and H a hydrogen atom. A connecting segment shows a chemical bond. All right, so it's been a very, very long time since I've taken chemistry, but I think I do remember at least this much, that when you write something like CH4, that stands for C1H4, 1 carbon atom, 4 hydrogen atoms. Okay. So here's methane, which has 1 carbon and 4 hydrogen. Here's ethane, which is 2 carbon and 6 hydrogen. And here's propane, which is 3 carbon and 8 hydrogen. So let's see, what is the question? Hectane is an alkane with 100 carbon atoms. How many hydrogen atoms does hectane have? Okay. So let's look at the pattern between number of carbon atoms and number of hydrogen atoms. Study the drawing of the alkanes and disregard the extreme left and right hydrogen atoms in each. So looking back at the picture, if you ignore the ones on the end, then when there's 1 carbon, you have 2 hydrogen. When there's 2 carbon, you have 4 hydrogen. When there's 3 carbon, you have 6 hydrogen. So that's a very simple pattern, right? The number of hydrogen atoms directly above and below the carbon is 2 times the number of carbon. And then, so with this restriction, we see that for every carbon atom, there are 2 hydrogen atoms. Therefore, there are twice as many hydrogen atoms as carbon atoms, plus the 2 hydrogen atoms at the extremes. All right. So in other words, we're thinking that this is the formula for the number of hydrogen atoms. So let's see if that works. If there's 1 carbon, you have 2 times 1 plus 2, which is 4 hydrogen. If there's 2 carbon, you have 2 times 2 plus 2, which is 6. And if there's 3 carbon, you have 2 times 3 plus 2, which is 8. So that does hold up with the picture that we were looking at earlier. And as long as that pattern holds up, if there are 100 carbon atoms, you would have 202 hydrogen atoms. Okay, and here's the formula, 2n plus 2. All right, here's a little slide that I added because I noticed them using this formula in the next example. We can examine a pattern to find a formula for the nth term of an arithmetic sequence with first term a sub 1 and common difference d. So this is a sad fact of math, right? Everybody complains about the letters in math. The letters are just placeholders for numbers. That's all they are. So I like to think of them like pronouns. You know, when you're talking about a person that hasn't been specified, you might say he, she, or they. And then, you know, once you're talking about a specific person, you might say John or Mary, right? That's kind of how these letters work in math, all right? They're just placeholders. So when n is 1, the nth term, in other words, the first term of the arithmetic sequence would just be the number a sub 1. A sub 1 is the first term of the sequence. When you go to the second term, remember, in an arithmetic sequence, the way you get from one term to the next is by adding the difference. So that means a sub 1 plus d, okay? Now I added a little something over here just to help the pattern come out a little more clearly. A sub 1 plus d can also be written as a sub 1 plus 1d, all right? Keep your eye on this number here, and then the number that's attached to the d, okay? When n is 3, you're adding another d, you're adding the difference again. So that would bring you up to a sub 1 plus 2d. And then when you get to n equals 4, you would have a sub 1 plus 3d. So each time you add another d, the coefficient on the d goes up by 1. All right, so for just general non-specified number n, the nth term would be a sub 1 plus n minus 1 times d. All right, notice, let me scribble on this a little bit. Notice that the number here, let me put it this way, the number here is always 1 less than the number that's over here, right? So 2 is 1 less than 3, and 3 is 1 less than 4. Okay. And that pattern does hold up. So you might want to make a note of this formula. You're probably going to be using it. Actually, I didn't really need to circle that n over there. Okay. That is the nth term of an arithmetic sequence. Okay, so now if I get, let's see, get rid of my scribble here, and we will go on to the next example. A theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. If the last row has 144 seats, how many rows are there in the theater? Okay. So we'll use the formula that we just developed. So in this problem, a sub 1 is 20, a sub n, the nth term, is 144, and d, the common difference, is 4. All right, so if there's 20 seats in the first row and 4 additional seats in each consecutive row, that means there's 24 in the second row, and 28 in the third row, and 32 in the fourth row. We're always adding 4. So that makes 4 the difference. So here's our formula. A sub n equals a sub 1 plus n minus 1 times d. We know everything except n. So we have to solve this thing for n. All right, so when we replace a sub n with 144, and we replace a sub 1 with 20, and we replace d with 4, we get 144 equals 20 plus n minus 1 times 4. And so now if we subtract 20 from both sides, we get 124 equals n minus 1 times 4. Divide both sides by 4, and you get 31 equals n minus 1. Finally, add 1 to both sides. You get n equals 32. So there are 32 rows in this theater. That brings us to the Fibonacci sequence. The Fibonacci sequence is really, really fascinating. All right, the ancient Greeks knew about the Fibonacci sequence, and they noticed it in architecture and art and nature. It's really, really cool. The next time you're down, a Google rabbit hole, that's what I call it, when you're just sitting there and you don't really have a lot to do and just kind of questions are popping into your mind. Do a little bit of reading on the Fibonacci sequence. It's really, really cool stuff. So the Fibonacci sequence is defined by the first term is 1, the second term is 1, and then after that, the way that you get each additional term is to add the 2 previous terms. And that's how this is how we write that mathematically. F sub n equals f sub n minus 1 plus f sub n minus 2. So for example, replace n with 3. You get f sub 3 equals f sub 2 plus f sub 1. And we know that there's f sub 1 and f sub 2. So 1 plus 1 would give you 2. So now we know f sub 3 is 2. F sub 4 would be f sub 3 plus f sub 2. That would be 2 plus 1, which is 3. And really the simplest way to do it is to just start writing them down, and every time you need a new number, just add the previous 2. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, et cetera, et cetera, et cetera. That's called the Fibonacci sequence. Next, we have geometric sequences. So a geometric sequence, the idea is kind of similar to an arithmetic sequence, except instead of having a common difference, it has a common ratio. To get from one term to the next, you multiply by a specific number. And that number should not be 0 because that would be really boring, right? As soon as you multiply by 0, it just becomes 0. So an example of a geometric sequence is 2, 6, 18, 54, 162. To get from one term to the next, you multiply by 3. In order to talk about geometric sequences, you need to talk about exponents. So this is almost definitely a reminder, right, of what exponents mean. If n is a natural number, then a to the power n is defined to be a times a times a, blah, 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 times a. All right, n of those, n factors. And special rule that you may or may not have forgotten from beginning algebra, anything to the power 0 is 1, except for 0 to the power 0, that's undefined. But any other number to the power 0 is 1. Other sequences, here's an example. Figurate numbers are, so think of the word figure, are sequences of numbers that can be represented by dots arranged in the shape of geometric figures. So for example, triangular numbers look like this. You arrange dots in a triangle and you get a sequence that looks like 1, 3, 6, 10. Of course, you already know about square numbers. If you arrange the dots in a square, then you get your perfect squares, 1, 4, 9, 16, et cetera, et cetera. All right, and we'll finish with this example. Use differences to find a pattern. Then, assuming that the pattern discovered continues, find the 7th term in the sequence. So when you first look at this, it looks kind of random, right? There's no pattern that jumps out, at least not at me. All right. So one really common trick for finding a pattern is by looking at differences. So here's what I mean by that. If you look at the differences between each pair of consecutive numbers, you come up with this. 6 minus 5 is 1, 14 minus 6 is 8, 29 minus 14 is 15, et cetera, et cetera. And then you just keep doing that until you do get a really clear pattern. So if we do that one more time, oh, look at that. It turns out that 1, 8, 15, 22, 29 is actually an arithmetic sequence with a difference of 7. So what I'm going to, well, let me bring this paragraph up, and then I'm going to switch over to my tablet because I think that you might follow that a little bit easier than this written explanation. The first difference, meaning the 1, 8, 15, 22, 29, is an arithmetic sequence with difference 7. The 6th term in the first difference, this number that would be here if we continued it, would be 36, which is 7 more than 29. And the 7th term in the original sequence would be 80 plus 36, which is 116. So if you had trouble following that, let me switch over to my tablet where I have written down this diagram. And so what I'm going to do now is just show you what they were talking about. So if you put another difference of 7 right here, that would make this number a 36. Which means that this number over here has to be 80 plus 36, which is 116. And that is going to do it for section 1-2. We are already done with chapter 1. Woohoo! So we'll start chapter 2 next time.